Okay, welcome to this lesson. We'll be learning on, we'll be introducing ourselves to electric circuits. We'll also look at formulas which are of importance when you are dealing with electric circuits. This is a group task that we have undertaken together with Catherine NDEGE, SHADRACK, who is the presenter, BILDAD SAPANIA, WINNIE MOMANYI, and DUNCAN SINDE. Without wasting time, let's start on the learning on the subject matter of the day. And what we need to know is what do we understand by the term electricity? Electricity in its simplest can be described as a flow of charge around a circuit. Every material in nature contains two fundamental units of charge. That it can either be positively charged because of the protons abundance, or negatively charged because of the electron abundance. And these two items, which is electrons and protons, their constitution within an atom can make an atom either be positively charged or negatively charged, and in a very small exception, to be neutrally charged or have no charge at all. And in that case, we'll be talking about the stable elements that are in the eighth rank. Now, electricity can be defined in its simplest as, or can be realized as a result of flow of electrons. So electrons in motion essentially constitute what you call electricity. When we use those electrons that are moving in a circuit, when you use it effectively to do some work, then we'll have effectively used this electricity to simplify our life. Now, the next slide is the structure of the atom, and here we look at what makes what makes electricity flow. And in this case, we look at the way that atom is structured. And in an atom, we have three different components. We have what we call protons, which are in the nucleus. We have what we call neutrons, which are in the nucleus. And then we have what we call electrons. And electrons usually surround the nucleus in what we call orbitals, have p orbital, s orbital, and the like. And these in simplest are called shells. Now, electrons surround the nucleus in varying orbits or shells, and the outermost shell is of interest to us as electrical or students who are studying electronics, because this outermost shell, which is also called the valence shell, is able to release that electron, which is able to flow, and by flowing carry out the tasks, or essentially become electricity. Now, the valence band is, as stated, the outermost energy level or the outermost shell in which an electron can exist. And because of the distance from the nucleus, these valence band electrons usually are not tightly bound as the inner electrons to the nucleus. So this shell, or this band, allows electrons to jump over them, depending on the size of the forbidden gap, to become to allow the electron be in the conduction band, and by so doing, it's able to allow electricity to flow. Now, just to simplify what I've just stated, the diagram that we have on the side is of a carbon atom. A carbon atom has 6 electrons. The innermost energy level has 2, and then the outermost has 4. And the force of attraction for the outer 4 is not as tightly as for the inner 2. Therefore, some of these electrons can escape from the atom, or from the molecule that this atom forms. And usually carbon combines with 2 additional carbon atoms, to form a three-band system where we have, and in such a case, we'll have a few electrons which are not entirely used in the bonding process, and these electrons can be free to move about. Now, talking about the valence band and the conduction band, which are already stated, uh, we already know that the valence band is the outermost orbit around an atom. If an electron gains sufficient energy, it is able to escape this band, and usually it can get energy from the surrounding, maybe the temperature, pressure, and at times even the way that electron is vibrating, and this is a complex aspect. Usually when electrons are moving around the nucleus, they are moving in a cloud, and they don't go in a perfect orbit. They usually vibrate. So for conductors, when these electrons are vibrating, at times they are able to gain sufficient energy to cross over to the conduction band. Now, the gap between the valence band and the conduction band is what we call the forbidden energy gap. For insulators, this gap is substantially large, so that the electron will need a lot of energy to jump over. And for conductors, this band is very, very narrow, and in such a, sometimes it actually even overlaps with the valence band, so that the electron can easily move to the conduction band without a lot of effort. So as shown on the graphic, we have the insulator. You can see the size of the gap. We have the semiconductor, which has a substantially small gap compared to the insulator, but not as small as the one for conductors. And that is why semiconductors can conduct electricity under very, very specific circumstances, because in those special circumstances, the gap through a doping agent, it's possible to reduce the valence, the forbidden gap, so that the electron can jump. And at times, based on the doping item, you can also increase the gap so that the electron cannot jump over, and thus we are not able to produce electricity. And thus, what semiconductors at times conduct electricity very well, and in some cases may not conduct electricity very, very well. Moving on. We've just talked about the conduction band and the valence band, and when you look at it from a molecule point of view, this is the kind of setup that you'll most likely observe, where when the electron jumps from the valence band to the conduction band, it is almost immediately attracted by another atom, and it fills the gap that atom had when its electron shifted. So in this case, you'll find that the electrons will be moving towards the positive terminal, and the holes will tend to appear moving towards the negative terminal. Remember that the electrons are negatively charged, so they are attracted to the positive terminal, and holes being positively charged will tend to move towards the negative terminal. So because of the way electrons jump and move about, there will be that apparent flow of electrons in a conductor. Moving on, now that we've looked at electrons, for when a single electron moves, it does not contain its capacity of being made to do some useful job is very, very small. So we always look at the flow of electrons in a much larger quantity. We always talk about charge. Now, for electricity to be of any use, we have to have a substantial flow of charge around a circuit, and charge is denoted by the letter Q. Charge is actually like a collection of billions of electrons moving concurrently around a circuit as a result of pull or push of an electromotive force. Charge is measured in what we call coulombs, and one coulomb is equivalent to 6.25 times 10 raised to power 18 electrons. Moving on, the thing that attracts us to use electricity is its ability to do work. The potential in this case refers to the possibility of something to do some work. A charge has a potential of doing some work, but a charge of a single electron is very minuscule. When you talk about one coulomb, for example, then it is quite substantial. It's substantial and it's able to do a considerable amount of work compared to the charge of a single electron. Now, charge can do work when it is in motion, when it is moving from one point to another. And for us to do that, we have to find a way of moving this charge around a circuit, and we'll use what we call electromotive force. And this is an electrical potential produced either by a battery or an electrochemical cell, or changing magnetic field, and this force pushes electrons to flow around a circuit. And when the electrons flow around the circuit, they are now able to be of some use. Now, usually we'll find that an electromotive force source or an EMF source will either be a battery or an alternating current source or something else. But the most crucial aspect about this type of force is that it is able to push electrons and make it move throughout the circuit. A good example is something like a battery. When you connect a conductor around the terminals of a battery, the electrons in that particular conductor are going to be attracted to the positive terminal, while the holes will tend to move to the other side. So actually what you are trying to induce, you're pushing electrons from the positive side, from the negative side to the positive side, and the holes from the positive side to the negative side, so that by that we have the flow of electrons. Now, when the work done by electromotive force is measured in a unit called volts, and this is named after Alessandro Volta. Alessandro Volta established that it is possible for us to measure the amount of work done by electricity, and he was able to come up with a unit that allowed us to that allows us to quantify the amount of work that some electricity can do. And by definition, he stated that when 0.7376 foot-pounds of work is required to move 6.25 times 10 raised to power 18 electrons between any 2 points, then the potential difference between those 2 points is said to be 1 volt. If you look at it carefully, 0.7376 foot-pounds is equivalent to 1 joule, and 6.25 times 10 raised to power 18 is equivalent to 1 coulomb. Therefore, the volt V, which is actually denoted by V, is equivalent to 1 joule per 1 unit of charge, or 1 coulomb, and this conventionally is represented by W over Q, where W represents the energy or the work in joules. Through that we have arrived at our first formula, which is V is equals to W over Q. Now the next aspect is current. Current actually is the measure of the amount of electrons that are able to flow at a particular time. Actually, in simple term, it's the measure of rate of a measure of rate of flow of electrons through a conductor. And because we are measuring the rate of flow, it will be the amount of charge that is able to move through a conductor, a particular point of a conductor, per unit time. And in this case, we'll be measuring it in terms of the amount of charge in coulombs per unit time, which is in form of seconds. When measuring current, we always measure it in amperes, and this unit is named after Andre M. Ampere, who's also shown there. Moving on, whenever we have current moving or electrons moving in mass on a conductor, there will be some opposition to this flow of electrons, and this opposition is what we call resistance, and this is actually denoted by the letter R. It can be defined as the opposition which limits the amount of current that can be produced by applied voltage. Remember that the voltage is the force that forces the electrons to move in a circuit, and the current is the rate of flow of electrons per unit time. So resistance is measured in a unit called ohms, which is named after George Simon Ohm, and this individual actually came up with another fundamental law that we're going to look at in a short while, which is called the Ohm's law. When we talk about conductors, you'll find that conductors have very, very little resistance. It's impossible to have a conductor without any resistance. The amount of resistance in conductors is very, very small, though there is still some amount of resistance. When you talk about insulators, insulators have a very, very large amount of resistance, and therefore you'll find that electrons cannot be able to flow. And because electrons cannot be able to flow, then such components cannot allow electricity to flow through them. Now, when we look at the inverse of conductor resistance, is something we call conductance, and this is also a unit that is used to measure how effectively electricity can move through a conductor. The higher the conductance, the better the conductor. The lower the conductance, the more poorer the conductor, or it can now be referred to as an insulator. The term conductance is measured in Siemens, and this is named after Ernst von Siemens, who was a German inventor who's shown. And the conductance actually is represented by the letter G, and I said conductance is equivalent to 1 over resistance, and it is measured 1 over R is equivalent to 1 Siemens, assuming that the resistance is 1 ohm. Now, with all those relations in mind, then let's look at the next aspect, which is the Joule's law. Now, the unit of electric power is what we call a watt, and this is named after James Watt, who is shown there. 1 watt of power is equals to work done in 1 second by 1 volt of potential difference moving 1 coulomb of charge. That means I have a PD of 1 volt and I have a charge of 1 coulomb. How much the work this can do is equivalent to 1 watt. Now, considering that 1 coulomb per second is an ampere, therefore power in watts is equivalent to the product of volts times amperes, or P is equals to V times I. Now, when you look at this equation, you'll discover that already now we have the relationship between voltage and current, and we can get, when we have the product of the voltage and current, we can get the power. But also, we can get the voltage given power and the current, or we can get current given power and the voltage. This relationship will come up or will be visited in a later slide. Another law that is crucial for us, as stated earlier, is what we call the Ohm's law, and this is the mathematical relationship between voltage, current, and resistance, and it was discovered by George Simon Ohm in 1826. This actually forms the basic foundation of all circuit analysis in electronics. Now, Ohm's law states that the current between 2 points is directly proportional to the voltage and inversely proportional to resistance, as long as the temperature and pressure remain constant. Or, in other terms, I is equivalent to V over R. And when you look at again this equation, we can deduce that resistance is equivalent to voltage divided by current, or voltage is equivalent to current times resistance. Now, with the two laws, that is the Joule's law and the Ohm's law, we are able to arrive at this circle, which denotes the relationship that we have regarding power, current, resistance, and voltage. And for example, if you look at the power, we have power being given by voltage times current, power also being given by voltage squared divided by resistance, power also being given by current squared multiplied by resistance. And when you look at the current is given by voltage over resistance as per Ohm's law. Using the power law, current is given by power over voltage, and substituting the power law in the Joule's law in the Ohm's law, we can also get that current is equivalent to the root of power divided by resistance. And the same holds on the other units, that is the resistance in ohms, where we have resistance is equivalent to voltage squared divided by power. Resistance also is equivalent to voltage divided by current, and also resistance equivalent to power divided by current squared. And on the other side, voltage is equivalent to current multiplied by resistance, or it is equivalent to the root of the product of power and resistance, or voltage can also be gotten by power divided by current. So all these relations can be put together, and given a situation where you've been given a consumption in, for example, maybe you are told some amount of charge is moving, and you are supposed to calculate the voltage, and you've been given either the power or resistance or the current, then you should be able to do it. And that marks the end of the introduction to electric circuits. In the next session, we'll talk about the direct current and the alternating current. Until that time, have a nice day. Any inquiries can be sent through the comments, and in case you have additional inquiry, you can always contact us through the emails attached. Thank you and have a nice day. The references were that we used were Basic Electronics Theory and Practice by S. Wiscott and J.R. Wiscott. That was the second edition. And then Michael E. Schools Group's Basic Electronics, that is the 11th edition. Have a nice day.